Hey guys, Mr. Roach here, ya boy. I am helping out my sister today. She's not feeling well. If she's with you, she doesn't have a voice. And if she's not in class today, it's because she doesn't have a voice. So I told her I would help her out. I have your notes here. I used to teach algebra. I actually teach higher algebra right now at MMW. So I'm your guide today. Follow along. I would encourage you to pause and maybe try some questions ahead of me if you feel like you're catching on to this stuff. And then you can resume me and see if you got it right. Today we're talking compound inequalities. Questionable meme here, I suppose, but hopefully you get excited to do compound inequalities because they are quite interesting. I'm going to kind of go right into the meat of the lesson, the meat of the notes here. When we link two inequalities together, we call them a compound inequality. Now, when I've taught this at the past, I used to teach algebra at the high school. I've taught algebra in some other schools that I used to work at before. I always talk about compound words. So some compound words would look like this. Butterfly. I have two words that are stuck together. Butter is a food. Fly is an insect. Butterfly, put it together. I've never eaten a butterfly before, but who knows why they're called that. But it is a compound word. I have two words on their own that have individual meaning, and when I put them together, I've got a new meaning. Do you want to know the opposite of a firefly? A compound word would, of course, be a waterfall. Fire is something. Fly, again, is something. Put them together, I've got a brand new meaning. Waterfall, same thing. Fire truck is another one that comes to mind. Like I said, compound would be two things with their own individual significance and putting them together. We've got two kinds of compounds inequality. We have ors and we have ands, and they work a little bit differently, but kind of at the center of it is I have this guy with its own meaning. X is less than negative 2 is right here. Literally give me any value smaller than negative 2 and you'll be good to go. And separately on its own, x is greater than or equal to 3. We've got that closed circle. We've got every value greater than 3. On their own, they have their own meaning, but together we can graph them as one kind of big problem. The other kind that we have are ands. Ands are pretty interesting because they're very specific. You have to satisfy both. I always say, I need a cheeseburger and French fries. You have to bring me both. If you only brought me one, it's not going to work. So an example is 7. Is 7 greater than negative 2? Absolutely. There's your cheeseburger. But is 7 less than 3? No, of course not. So you brought me the cheeseburger, but not the French fries, and now I'm mad, right? Or you brought me a cheeseburger and a milkshake, but I wanted French fries. So you have to satisfy both, which is why we see this kind of interesting, like line segment almost. X is greater than negative 2 would be this line that goes on forever, but it gets stopped, it gets chopped off at x is less than 3, which is going back that way. And so we kind of get this, like I said, kind of like a line segment. Or is very open-ended. So ands, you have to satisfy both conditions. Ors are very open-ended. I go to a restaurant, I say, hey, give me a cheeseburger or French fries. If you bring me one, great. If you bring me only French fries, I can't be mad. I have to be happy. If you bring me both, that's great. But I really only wanted one of them. So 7 is another good example. Is 7 less than negative 2? No, but it is greater than 3, so 7 is a solution to this one, right? 7 would be out here. So ors, we have very general, very non-specific. Ands, you have to satisfy both. We're going to take a look at ands. This page kind of summarizes what I just said. Here's a compound inequality. I've got x is less than 4 on its own would look like this. Open circle at 4, any value less than there, 3, 2, 1, negative 8, negative 44, it doesn't really matter. But you also have to satisfy x is greater than or equal to 2. You have to be both of these things, which looks like that. When we stick them together, this orange guy is going to get stopped by the blue guy, and the blue guy, vice versa, will get stopped by this orange boundary point. So we end up with this intersection. So you're kind of combining two graphs into one. You're combining butter and fly, and you've got butterfly down here. Some cool notation with this is we can, with ands, we can kind of bring it into one notation. We see this notation a lot in higher algebra. In the class that I teach, is we go from smallest to biggest. You'll notice that these compounds are still here. This is x is greater than or equal to 2. It's written backwards, but it's still there. And I have x is less than 4, which is still there. I read this out loud myself as x is greater than or equal to 2. And x is less than 4. Some people might do a little differently than me, but we have this cool notation for compound, and we can split these apart, like I said, into their own version. I've got this guy happening, and I've got x is less than 4 happening. One quick note that I like to remind my higher algebra students, we always go smallest to biggest, right? We want to organize from left to right, just like our number line is organized. So 2 would go on the left, and 4 would have to go on the right for these and properties. Okay, let's take a look at some solid examples. I'm going to do this one, and then I'm going to actually jump down. I'm going to save this one for later. But here is a compound inequality. This special notation tells me that it's an and inequality, so it's probably going to be those two lines going together. Over here, I've got one inequality that looks like this. X plus 1 is greater than negative 5. So if I just take a quick second to solve it, I'd have x is greater than negative 6. And graphing-wise, it would look like this. Open circle, arrow going to the numbers bigger than negative 6. That's my first inequality, right? Compound inequalities are 2 put together, so I'm just kind of breaking it down to one at a time. My second one, I'll do in this reddish color, would be x plus 1 is less than 2. Quick solve, x is less than 1. So if I were to plot this on the same, oops, I missed a couple numbers there. If I were to plot this on the same number line, open circle, going to the left, all the numbers less than 1. And I've got these two inequalities that are coming down to crash into each other. So it'd be better if I simplified it, so to say, and just wrote one segment from negative 6 to positive 1. Both open circles there. My final inequality would be sticking these two together. I would say, hey, x has to be greater than negative 6. And at the same time, x is less than 1. The one right below it, and again, feel free to pause if you feel like you're catching on to this, if you want to try this on your own. The one right below it is a little bit of the reverse, is it already has a finished product. I'm seeing two inequalities crashing into each other. And normally they would go on forever and ever, but green is going to run into the red open circle, red's going to run into the green open circle. So I'm seeing two things. I'm seeing x is greater than negative 2. That would be the red one. And the green one is x is less than 5. If I'm going to put it into that fancy notation, I'm going to go smallest to biggest. There's x is greater than 2, and there's x is less than 5. Sometimes you'll see the word and put in between them. That's also okay. I would say this is more simplified, more standard way of writing it. Just to show you one more, I've got this part of my inequality being x is greater than or equal to negative 9. Got that filled in circle there. And this part of my inequality, x is less than, strictly less than negative 2. And there's my inequality shown on the graph. Most typically, you will see inequalities where one is a less than and one is a greater than. The reason why I skipped this one right away, coming back to it now, is because these are both greater thans. Kind of an interesting problem. It's still a compound inequality because I want you to consider both at the same time. I'm going to solve them separately anyway, right? We're just going to kind of graph them together at the same time. This one, which I'm doing in green, is going to be x is greater than 4. And this one that I'm going to do in orange is going to be x is greater than 6. Now you have to satisfy both, right? I need a cheeseburger and French fries. So if I said, hey, could x be 5? And if you plug it into there, sure, that's great. 5 is bigger than 4, but it doesn't work for this one. So what's kind of interesting is you just graph the overlapping part. If I were to put this on a number line, green would show up like this, orange would show up like this, but I'm really only interested where the green and the orange are on top of each other. All of this stuff is a cheeseburger but no French fries, right? So that stuff isn't going to work. So if I'm graphing this, your final inequality is going to look like that. There's not as clean of a way to write this. I don't love the idea of saying, hey, x is bigger than 4 and x is bigger than 6. We don't typically do that, which is why you see the word and put in between them. So ands, we're looking for overlaps. Ands have a nicer notation where like this one is a greater than and a less than. Ands have that nicer notation of x is greater than 2 and x is less than 6 put together like that. And then again, pro tip written down here, I would probably just do the graph first and I would do them both individually. So like, hey, x is greater than 2 would be here. X is less than 6 would be here. And I'm just going to graph the overlap. This one would look like that. Now would be a good time to pause, ask Mrs. Mullen or whoever is there questions about compounds inequality. I don't know, just make sure that you're feeling good about these before I move on. We do have another one to look at, and that's ORs. ORs are the very, very not specific. There are so many solutions to this, y'all. And literally any number less than 2 or any number greater than or equal to 4. That is so many things, infinite many things in both directions. Is quite interesting. My trick is that oars usually look like oars on a boat, is that they're going off to the side. Here's my attempt at a boat from the front. That's not bad. The boat is facing you and the oars are coming off to the side. I don't know. It helps some students remember that oars go over the edges of the boats. They go away from each other very typically, but it works the same thing. Is I've got this inequality, I've got that inequality, and now let's consider them together. Just taking a look at this one, I have to ask Mrs. Mullen, but these look like the same problem. So I'm going to go ahead and I'm going to skip down, get you to work time a little bit faster. Ors, we don't have the fancy notation like ands. We don't see this stuff for ors. Ors, we have to use the word or to communicate them. So if I'm going to represent this with algebra, I would say x is less than 2, and then I would have to include the word or. X is greater than 6. And then like I just said with the graphs, they're going to look like oars on a ship where one goes to the right, one goes to the left, and they're not going to crash into each other. Lots of different answers here. This one is x is less than 2. This one is x is greater than 6. Here's a more fleshed out example. Be very careful of your negatives on this one if you pause and you work ahead. I think that would be a good idea. 2 inequalities, so I'm going to treat them like separate inequalities, and then I'm going to have to graph them together. That's what makes them compound. Take a look at the difference between them. This is a good reminder of when do we switch the inequality is when you divide by a negative. So this one, I'm dividing by 3. This one would not switch. This would be x is less than -3 and would graph like that. Orange here, I would divide by -4. My action that I'm doing is division by -4. So it's not that this number is negative, but it's the one I'm doing to both sides. This is going to flip and x would be greater than 1. Would look like that. And I've got my oars on the boats going away from each other. A couple more or inequalities. We can go through these pretty quickly. Hopefully you're catching on. Again, notice we don't see any of that fancy notation. We literally see the word or in between them. Again, 2 separate inequalities. So I'm going to treat them like separate inequalities, and then I'm going to go ahead and graph them together. This would be t is less than or equal to -1, filled in circle. Oh, greater than. Sorry, I messed that one up. Greater than, filled in circle. Going to the right, this one, subtract 8, t is less than -6. I'm gonna have to give myself more room. Just read that one wrong right away. Let's move that guy down there. -3. Oh, Mr. Roach, you're struggling right now. There we go. -3, -4, -5, -6. This is like the dilemma all teachers face. Like you just screwed up, but you're like 12 minutes into this video. Do you really make a new one? Probably not. Sorry, you're gonna have to live with my incompetence. This guy here, I'm not switching anything. I see negatives involved, but I am dividing by a +2. So this one's going to stay put as y is equal or greater than -4. And this one here, y is also greater than -4. Kind of a weird one. You could be either, and they're kind of the same equation written twice. Your oars are just going off the same side of the boat, which is fine. We can do that. Okay, again, one more time, just to summarize oars. Oars, I can tell this is an or because they're going away from each other, and I don't have like a fancy notation way of writing this. I'm just going to say, hey, x is less than or equal to -3, and then I'm going to use the word or to communicate that this is an or. X is greater than or equal to 2. Last one here, x is less than or equal to -8, the word or. X is strictly greater than 0, no equal sign there. We've got that open circle. Good summary for you here. Good way to, I don't know, kind of review what we just talked about. We've got just one more page of examples and then I will be done. If I'm looking at, this is a great way of summarizing how I can identify which is which. This fancy notation tells me that this is an and problem and that I'm going to end up with something that looks like that. On the left, I literally see the word or, which tells me it's going to be an or problem. Maybe you want to pause this and see if you can beat me to the answer. But here's me working this one out. If you did pause, make sure you did a flip on this one. I'm dividing by -3, and I've got k is less than -3. So here's my green inequality, the one I solved on the right. Here's my gray inequality, the one I solved on the left. As a compound inequality, we are considering both of those together. This one is an and inequality. Again, I can treat them like 2 separate inequalities. I'll pull them apart and say n plus 6 is greater than 4 and n plus 6 is less than 9. Subtract 6, subtract 6. I've got n is greater than -2. And again, subtract 6, n is less than 3. So if I erase my scratch work so I can see, I'd have 2 open circles and a line connecting them. A little bit interesting here with some no solution examples. We are interested in overlaps. We are interested where both of them are true. So this guy came out here, and this guy came out here, which is why we graphed that orange solution where the overlaps. This is a no solution because it would never overlap. It's written like an and, but notice the inequalities are backwards. So I have, hey, x plus 2 is greater than 1. So this one says I need any x value greater than -1. Whereas this guy says x plus 2 is less than -5. But like, tell me an x value that is both less than -7 and greater than -1. That's not possible. If I were to graph this on a number line, just to show you a quick sketch, this one would go that way, and this one would go that way. It looks like an or, but it's written like an and. No solution. There's nowhere that this guy overlaps. Again, written like an and. And this would be the same thing, is I'm going to solve it, and I'm going to end up with a situation where it's written as an and, but it graphs like an or. So I'm somehow supposed to satisfy both conditions, but any solution for this blue guy is not going to work for that green guy as well, right? I'm going to have no overlap of the solutions. Ands are really where you're going to be looking out for these no solution examples. Ands are very, 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 very specific. And if you don't satisfy both conditions, you're not going to make your customer happy, right? I can get them a cheeseburger, but I can't get them French fries. The fryer's broken. Sorry. Anyway, ask questions, bring questions to class tomorrow with Mrs. Mullen. Email her about flex time or come in before school. We also have Mr. G around. There's an intro to compound inequalities. I'm sure you will continue working on that in the future. Have a great rest of your day.